created by MindSticks Foundation Trust. Hello, students, and a very warm welcome to today's explainer session. Today, we're going to build our mathematical toolkit step by step. We'll start with some core concepts: the basic proportionality theorem, the angle bisector property, and 3 parallel lines. Then we'll wrap it all up with a quick summary and tackle a practice problem together. All right, let's dive into part 1. We're introducing our very first and honestly most crucial tool today, the basic proportionality theorem, or BPT for short. Now, I'll read this out, and I just want you to let the geometry logic really sink in. It states, if a line parallel to a side of a triangle intersects the remaining sides in 2 distinct points, then the line divides the sides in the same proportion. Take a moment to digest that. The absolute key phrases you've got to remember here are parallel to a side and same proportion. Let's see how the visual proves these words. I want you to carefully observe this figure on your screen. Notice how that line L slices horizontally right through the triangle. It intersects sides AB and AC at points P and Q. And because this line L is drawn strictly parallel to the base, BC, it creates a very special, highly useful, proportional relationship between the segments it just cut. So, how do we actually prove this? Well, step 1, we draw segments PC and BQ. This neat little construction gives us triangles of equal heights. Step 2, we use what we already know about areas. We compare the area of triangle APQ to PQB and then APQ to PQC. And since triangles with equal heights have areas proportionate to their bases, we naturally flow right into step 3. We can mathematically conclude that the ratio of segment AP over PB is strictly equal to the ratio of AQ over QC. See? It all connects. Now, here is a crucial point, and it's a place where students often stumble, so pay close attention. We need to understand the difference between the theorem we just learned and its converse. The theorem tells us if you start with a parallel line, it guarantees proportional division. But the converse? It goes in the exact opposite direction. It tells us that if you discover a line divides 2 sides of a triangle in equal ratios, then that line absolutely must be parallel to the third side. Proportional division gives you a parallel line. Just make sure you don't get confused about which direction the logic flows, okay? Excellent work. Moving right along to part 2, let's shift our focus to the internal angles of a triangle. Here is our second major tool, the property of an angle bisector. It reads, the bisector of an angle of a triangle divides the side opposite to the angle in the ratio of the remaining sides. Now, don't let the slightly complex wording worry you. It simply means that if you slice an angle exactly in half, it creates a totally predictable ratio on the opposite side of the triangle. Let's guide our eyes to the figure here to make complete sense of this. Trace the path of ray CE with me. You can see by those identical markings at angle C that ray CE is splitting that angle perfectly in half, right? And it hits the opposite side, AB, at point E. So, our property tells us that the ratio of side AE over side EB is going to be equal to the ratio of side CA over side CB. To prove this, we first construct a line parallel to ray CE passing straight through point B. Next, we identify our equal, corresponding, and alternate angles, which neatly shows us that side CB is equal to side CD. And finally, for step 3, we do something truly wonderful. We apply our very first tool, the basic proportionality theorem, to the large outer triangle. This brilliantly illustrates how in mathematics, we're constantly using older tools to help us prove and build powerful new ones. You are grasping this so well. All right, let's move on to section 3, our third and final foundational theorem for today. This is the property of 3 parallel lines. It states, the ratio of the intercepts made on a transversal by 3 parallel lines is equal to the ratio of the corresponding intercepts made on any other transversal by the same parallel lines. Now, take a breath. It is absolutely essential here that you keep the distinction clear between the parallel lines doing the cutting and the slanted transversals that are being cut. Let's observe the 3 horizontal parallel lines here, L, M, and N. Now look at the 2 transversals, T1 and T2. Notice how the parallel lines basically chop transversal T1 into segments AB and BC? Well, in exactly the same way, they chop transversal T2 into segments PQ and QR. The theorem is just telling us that the ratio of AB over BC will perfectly equal the ratio of PQ over QR. And with that, I want to formally congratulate you all. You've successfully navigated the core concepts of this entire geometry chapter. So let's head into part 4 and summarize our essential toolkit. Before we attempt to solve any exercises, it's definitely time to review our completed master cheat sheet. Please look closely at this summary. I really want you to remember this page as it visually anchors all 4 properties we just painstakingly proved together. Whenever you feel stuck on a test, just close your eyes and picture this exact toolkit. Let's recite these formulas together rhythmically. It really is the best way to boost memory retention. Ready? Number 1, BPT. AP over PB equals AQ over QC. Number 2, converse of BPT. Proportional sides tell us that segment ST is parallel to QR. Number 3, angle bisector. AB over BC equals AD over DC. And number 4, property of parallel lines. AB over BC equals XY over YZ. Very, very good. Finally, section 5. It's time to roll up our sleeves for a practice problem walkthrough. I invite you to apply your newly built toolkit to mathematically solve a real problem from practice set 1.2. Let's read the problem statement deliberately. Question 2, in triangle PQR, segment PM is 15. The total length PQ is 25, total length PR is 20, and NR is 8. The question asks, state whether line NM is parallel to side RQ, and give a reason. Before we solve this, I want you to mentally guess, which specific tool from our kit are we going to need to prove lines are parallel? Here, I've drawn a direct visual comparison to help us out. On the left is the figure for our textbook problem, and on the right is a figure directly from our cheat sheet. By placing them side by side, it's so much easier to recognize the pattern. We need to use the converse of BPT, because as we remember, if we can prove the ratios are equal, we can prove the lines are parallel. Let's walk through the arithmetic step by step. Step 1, we must find the missing pieces. Since PR is 20 and NR is 8, PN must be 12. Since PQ is 25 and PM is 15, MQ must be 10. Simple subtraction. Step 2, we find the ratio of PN over NR. That's 12 divided by 8, which simplifies nicely to 3 over 2. Step 3, we find the ratio on the other side, PM over MQ. That is 15 divided by 10, which beautifully simplifies to exactly 3 over 2 as well. Step 4, since both ratios are identical, we can proudly conclude that line NM is indeed parallel to side RQ by the converse of the basic proportionality theorem. You see how simple it becomes when you use the right tool? Before we finish up today, I'm leaving you with this star-marked challenge as your homework. Question 11. In triangle ABC, ray BD bisects angle ABC and ray CE bisects angle ACB. If segment AB is congruent to segment AC, prove that ED is parallel to BC. Try combining the angle bisector property with the converse of BPT. Write down the equations, compare the ratios, and just watch the magic happen. I know for a fact you have the tools to solve this. Mathematics is just a giant puzzle waiting for the right tool. What other complex problems around you can be solved by simply drawing a parallel line? Thank you for joining me in this explainer session today, students. Keep practicing.